Okay. So thank you all for coming in this beautiful weather. My name is Amgad, and I know the talk was about improving object detection deep learning using Bayesian optimization. But I want to first take like a show of hand of how many of you guys have used convolutional neural network before? How many have used convolutional neural network before? Okay. So the question is, can we dial it back a little bit and talk about convolutional neural network in details, and then move to object detection using deep learning, and then the optimization part, or should we dive in directly to object detection? So I just want to get a feeling. But so what do you think? Convolutional neural network first? Okay. So just to see here. So first, this is part of an older talk I gave about convolutional neural network, but I'm gonna skip the feed forward part, and I'll be switching between two talks. So just bear with me. Okay, so convolutional neural network is using basically what's called filters or kernels to do two things. The first part is the convolution operation. The second part is the pooling operation. That's basically the two main operations that we use in a convolutional neural network. So if you look at these neurons over there, we have an input feature vector x1 to x4, and we're using what is called the local connectivity. So we're not looking at the whole feature space, we're just looking at a group of features together. So the first neuron will be looking at x1, x2, the second neuron will be looking at x3 and x4. And that's what is called local connectivity, and that's what actually makes the convolutional neural network. So the convolution operation using this local connectivity can be demonstrated like this. This is a 1D convolution, so we have some weights, W1, W2, W3, that will be connected to x1 to x3. And what we do is we convolve. So basically you multiply, you sum, and then you have the output. Multiply the values for x1, x2, x3 with the weights, sum, and then you have the output. So that's basically the output of a convolution operation, right? And then you slide this ahead, and basically you have the output y. So it's quite a simple operation. Now you can extend this into 2D, where we have, instead of having just a single 1D of weight, we have a 2D now. And that basically works very well with 2D inputs like images, for example. So now we have a convolution filter that have these weights, and we convolve this with the source pixel, and we have the target pixel by following this multiply and sum operation, right? And this is basically how it's done in 2D, very simple. We start with these pixels, we multiply, we sum, and then we have the output pixel out. Okay, so the idea of those convolution filters, right, is to do what is called a feature extraction. So we start with low-level features like ages, and for this example, we have this filter is detecting actually vertical ages, and this filter over there is actually detecting horizontal ages. So the whole idea is to come up with an automated way to extract features. Okay, so once we have learned one filter, we can extend this to n number of filters, and hopefully each filter of those will learn to detect a specific feature. So for example, filter 1 here is detecting the vertical edges. We have filter 2 horizontal, and then 45 degrees, and then 45 degrees. So, and we put all these together and we get a 3D volume which called a feature map. So that's the output of a convolution operation, right? We get a feature map. Okay, so the second process is very simple. It's called the pooling operation, and basically the main purpose of this operation is to reduce the complexity of the feature space. So instead of working on, let's say here, 3 by 3, it's 9 pixels, we will work by 2 by 2 by doing this pooling. So many other operations, the most widely used one is called max pooling, which basically you lay over this 3 by 3 region over the input image, and then you take the maximum out of it. And that's basically what you see here. So the red region is actually just represented by 1 pixel, which is 10. The green is represented by 9, the yellow 16, and the purple 7. So that is the max pooling. So a typical CNN architecture would look like this. We have a number of discrete, ordered, fixed size layers, L1 to L4, and these are convolutions. And basically the intuition is, hopefully, right, that the first layer will learn very low-level features like ages, for example, and then you start building a higher level representation of the thing that you're trying to work with. So in this case, we're trying to detect faces. So hopefully the second layer would learn like nose and eyes, eyebrows, and so on, and then you go a little bit for the object model, which is, in this case, the face, right? And typically the last couple of layers is a fully connected, which we usually use for classification. Okay, so that's it. So that's the convolution part. I need this because I've been talking about how we use deep learning to do the object detection. So do you have any questions on how the convolution work? Yeah.
So you say that the first level filters are locally cascaded.
Yeah.
That means, does it mean that they don't work on the entire image or just work on a part of the image?
Yeah, just I'll try to bring this up. Yeah, it's up. So so it's locally connected. So basically, you only look at the neighborhood beneath you, right? So if we have a filter of 3 by 3, we're only looking at the 3 by 3 region in the image, right?
But you tell me,
And then you slide, basically. And the local connectivity here, just you share the weights across the neighborhood that you're looking at. So that's it. Okay. Yep.
is CNN used only for image information or can it also be used for other type of data tables or?
Yeah. So yeah, that's a very good question. So basically, I'll just show this up. Okay. So basically, it's a 2D dimension, right? So that's the first thing, and the second thing is they have this. So if the features that you're trying to detect or work with differs as you move away, then you can easily use CNN on this. So for example, what we did in Danske Bank for transactional data, that's the credit card transaction, for example, is we tried to group them in a way that will mimic this feature. So as long as you move away from the features, then the correlation starts to decay. So anything that preserves this kind of feature can be used with CNN. So it's actually used for natural language processing as well. So it's any kind of data that you can put in this dimensions. Yeah. 2D is one. You can yeah. There's also 3D convolution as well. So it's this idea, the thing that you can put it in an X and Y, of course with depths, but then they have this kind of spatial correlation things around. Yeah. Okay, so that's the original talk. So how did we improve the region-based CNN object detectors using Bayesian optimization? So I'm going to talk about deep learning object detection, and then I will focus more on faster RCNN, which some sort of a state-of-the-art for object detection using deep learning. And finally, I'm going to discuss the Bayesian optimization, right? So and how did we use it to come up with what we call the local search algorithm to improve upon the faster RCNN. So let's go ahead. Deep learning object detection. Before we move to deep learning object detection, you need to think about classification task first. So classification is the question you're trying to answer is this image has a motorcycle in it or not, right? So if we, in a very nice world, we would just take this image, give it to a learning algorithm, and we will have our answer. But we don't work on raw pixels. Why? Because let's say that I'll take 2 raw pixels like these guys, right? And hopefully what I'm looking for is some sort of a separation between the positive class, which is the motorcycles, and the negative class, which is everything else. Hopefully that would be the case, but you know, we're not living in a perfect world, so this is the case. We don't work on raw pixels because everything is cluttered. So we need to insert something in the middle, which is feature representation. And that's the whole idea behind convolutional neural network, why it's very good, because it works really well when it comes to feature representation. But this is pre-deep learning, so I'm just give you an idea that we had to come up with algorithms that will describe the wheels, that will describe the handlebars. This is all hand engineered, right? So we had to come up with these ideas to move from this cluttered space to a very nice separable space between the wheels and the handlebars, right? So that's the computer vision. Most of the computer vision literature was around coming up with features that will easily describe the world around us. People spent a lot of time doing this manually. It was quite fun, but now we have deep learning. So first, the classification pipeline in general is we start from the raw pixels, then we go for low level, like this is hand engineered, then we go for a higher level representation, and finally we end up with a classifier that will classify the work we're trying to do, right? In a deep learning world, as you can see, that we build like this kind of ordered, discrete number of features, number of layers that actually composes a deep learning network, whether it's convolutional, whether it's a feed-forward, it doesn't matter. But basically, that's the whole idea. It takes these three separable steps into a single machine, right? But still, this machine does the same thing. It does feature extraction, higher level representation, and classification. It does the same thing. Okay. So moving from classification to object detection, now the question is, does this image contain a cat? Yes or no? But the detection is where the cat in the image. So basically, we need to put a bounding box. We need to know the coordinates where the cat is. And that's simply is object detection. And if you think about it this way, then we can break down the object detection into smaller classification jobs. If we look at a specific part of the image and then we slide, we basically each region or each window, we ask if this window is a cat or not, or this window is a car or not, and then we slide, and then we slide, and then we slide. So that's actually called the sliding window approach. And before deep learning, this approach was very easily used. But so if you look at an image at these dimensions, right, and we're looking at a window of 36 by 36, eventually we'll end up by around 430,000 images that we want to test for classification, right? This was very nice when we used the hand engineered jobs, because the hand engineered features was very well written. So basically, it is computed very fast on the CPU side. So dealing with this number wasn't a big issue. But when you try to bring in deep learning in the equation, and you want to send this data over from a CPU to a GPU, then this number is not going to work. So basically, that's too huge. So people came up with many other algorithms to try to reduce the number of regions that we are looking at. And one of them is a selective search. So basically, it segments the image. So you can see the first level of segmentation, we have a lot of regions, and then we have the output is a lot of regions in blue. Then we try to join the close by regions together, so we get a reduced number of regions, and then we and again until we reach a very reasonable number that we can work with. And this basically took us from 430K to 2K, which will do good enough. So with this selective search, using deep learning for object detection become a nice idea. We can do it. And the first people, so before I go through this, so the detection pipeline is simple. We take a bunch of regions, we extract the features, we compute the classification score, and if the classification score is too low, we discard. If it's too high, we keep it, and then we repeat, and so on and so forth. And then there's usually a step called non-maximal suppression, which does the cleanup for us in the end, but it's not the focus here. Anyways, so the first people that used the selective search to come up with a small number of regions to use deep learning for object detection was the people that came up with RCNN. So it's called region-based CNN object detector. So we start with an input image, right? And then we consult the selective search algorithm for, give me the best 2,000 regions that I can test here. And it gives us these regions. We warp those regions into a fixed width and height, right? And then we pass this into convolutional layer to extract the features. And then we train a support vector machine for classification and what is called the bounding box regressor for giving you the coordinates of this region in the output. So giving you a good coordinates about the dog or the cat or whatever. So that's the localization part. So you know that it's a dog, but you need to improve the localization by doing this bounding box regression. So the support vector machines will give you yes or no. The bounding box regressors will give you four coordinates, right? That's the RCNN. You can see that it had, like, still there are people involved, still there are, ad hoc steps. So basically we had to work with 3 different loss function, one for the log loss, one for the support vector machine, and actually one for the square loss for the bounding box regressors. And the training would almost take about 84 hours. So if you want to try a new idea, you have to wait. You have to wait. And this kind of prototyping was very, very, very slow. Yeah, so, and you can see that the testing pipeline, the experience of testing is a little bit more different than the experience of training because you had this ad hoc steps. Okay, so people came up with fast RCNN. And in this time, I'm going to start with the testing pipeline. So the testing pipeline is very similar, is very simple. So first, the first step is instead of consulting the selective search algorithm for regions, we first compute the whole features. Makes sense, because in the selective search, in the RCNN, we had to compute the features for each region, and that's actually very computationally expensive. But in this case, we compute the feature for the whole image at once, and then we ask the selective search algorithm for the regions, and we crop the features from the last feature map. That's basically cut the testing time like dramatically. Okay, so now we have the regions cut from the last feature map in different shape and sizes. We do some what is called an ROI pooling. It's also a nice idea just to try to fix the size and the width and the height for the regions. And then we feed for a fully connected layer which works as a classifier. And we had 2 heads: the softmax head, which give you distribution over the classes, which kind of object it is, and the linear regression, which gives you the 4 coordinates of the region, of the best region that fits this object, right? And that's basically the testing. So you get the probability for the class, and you get the location of the object. For training, all you have to do is just insert a log loss, which is the cost function, and then the whole architecture is trainable. So you don't have to cut anymore or do ad hoc training or anything like that. So the whole thing is trainable end to end. Okay, so both the RCNN and the fast RCNN did depend on external region proposal algorithm like selective search, right? So we can do better because these regions are not, optimized to minimize the network loss. They are just, we're asking someone external, don't know what kind of task we're trying to achieve. We're asking it to give us just some good region that they think they are. So basically, they were not tuned to the network loss, and we didn't have any control over the quality of the regions that we are testing. And basically, that's what they solved in faster RCNN. So it has two heads. It has 2 sibling networks. The first step is as fast RCNN. So we push the image through the convolutional layer for the feature extraction, and then we start to take 2 routes. The green one, and I will show you the other one. So the green one here is called region proposal network, which have 2 outputs. The first output is a binary classifier, which tells you, is this region contain an object or not? So it's a class agnostic. So I don't care about the object. I don't know if it's a dog, or I just know that there is an object. And the second one is, of course, the coordinates, right? So this is class agnostic region proposal network, so RDN, right? And this is the green path. And then once we train this green path, we come up with the region proposal. So now we don't need any external region proposal algorithm. We take whatever output from here, we project it again on the feature map, and we crop, we resize, and then we move to a fully connected layer. So basically, the green one is the new addition. The blue one is the fast RCNN. So that's basically faster RCNN. Okay, so both faster RCNN, fast RCNN, RCNN, they did a really good job when it comes to improving the region proposal. However, still, when you look at the best, the regions with the high score, that have the, like the objectiveness score, still when you project that back onto the feature map, you still see it is ill-localized. So it does not contain the object of interest perfectly, right? So I'll give you an example. So this is the bus. So when you take the rank 1 region, the region that have the highest score in terms of classification, you still see that it does not contain the object correctly. And this is a big problem when it comes, for example, to autonomous driving. You don't want to have a region that have, like part of the bus out, and then you crash into it, or a pedestrian or something like that. And it get even, more confusing when you take the top 3 regions, the top 500 regions, and then you get the top 100 regions. You see something like this. It's all over the place. So how can we improve this kind of localization issue, give you better regions? So we used Bayesian optimization. So and that's the optimization part of this talk. So any questions so far before I go to Bayesian optimization? Yeah.
Excuse me. So usually a softmax layer has some sort of predefined label set. You said that the softmax layer was agnostic.
Yeah. So in the region proposal, yes, it was. So so the green one is agnostic. It just gives you yes or no. It's a binary.
Okay.
Because you're just testing if it's an object or a background. That's it. And then you have the blue one, which will give you the different classes. Yeah.
Does the region proposal method give you one bounding box per pixel suggestion, or
I'm sorry.
you suggest you one bounding box per pixel?
Not per pixel.
I mean, you are really making it your bounding, so it's going to give you an object per pixel, no?
No, I don't get the question. Can you repeat it?
The region proposal network.
Yeah, this part, the green part.
Also, create a feature map that's where you have these features that are basically telling you that there is something, and it's going to be a bounding box suggestion.
Yes.
There's going to be a bounding box suggestion for every single pixel of the image. So
yeah, I get it. Yeah. So when you do this, this is the first layer of convolution net does this. We remember the convolution and the pooling, right? So the perception of the network for the image become a little bit more smaller, which in turn turns into a global look. So basically, as if you're not looking at pixel, you're looking now at the group of pixel. And the deeper you go, this perceptive fields become wider. So the outputs of the RBN would be on the last feature map, which actually looks not on pixel, but a group of pixels, depending on how deep you go on the network. So that's it. Yeah.
For the region proposal network,
Yeah.
do you know what the use of softmax and a sigma? Because it's binary, right?
Yeah, I know. Yeah, it's yeah, you're correct. But the downside of using softmax is that you double the number of parameters, because now you have 2 outputs, right? Instead of having just a single output for the log for the logistic, instead of having just a single output, now you have 2, right? That's a background and a foreground. So that's the downside of using softmax. But I think it's typically used, right? They use a softmax for a binary classification.
Can you frame these 2 networks simultaneously? Does it propagate to both at the same time?
Yeah, so they had, I think, 2 or 3 different training approaches. So the first approach would they train the RBN first and then freeze it and take whatever comes out and then train the blue pass. So they called it the alternative approach. And that's basically the one that they submitted for the paper. They continued the work on different approaches, but it's a little bit more complex, and the advantage was not that big. But basically, they alternate between the 2 networks. Yeah. Any other questions? Okay. So now for the Bayesian optimization. So people use Bayesian optimization for a black box optimizer. So what does this mean? If you have a function that have a formula, right, and you can access the gradient of this function, then basically Bayesian optimization is not the way to go. However, in this case, we didn't have access to the gradients because we had non-differentiable parameters, like, let's say, the number of filters or the size of each filter and all this kind of stuff. These are non-differentiable. So basically, we don't have an access for the gradients. So it's called a black box optimizer for this reason, right? And basically, what we need to do is now we want to maximize a function called an objective function. So all we have access to is something that we give it an input and we observe an output. That's it. So we follow a very simple steps. First, we create a model because we don't know the actual function. We create a model that will describe this objective function. And then we acquire the next point that we think will maximize this function, following what is called a posterior distribution over the function space. And we use what is called a utility function to give us this kind of guidance, right? So we need a model and we need a utility or an acquisition function, so these two parts. Then once we acquire, we evaluate. So we evaluate the new point using the objective function. We observe the true value of this point. And then we update the model because now we have a new evaluation. We have a ground truth. We update the model and basically we repeat. So create, acquire, evaluate, update, and repeat. And we keep doing this. Most of the literature says that after 20 evaluations or 20 iterations, you get at the maximum of this function, nothing more. So it's quite energy efficient. Okay, so we can extract two components of Bayesian optimization. The first one is the posterior distribution, which is the model that will describe the function. And this posterior distribution is divided into two things. The first part is the likelihood. I'm not going to talk about it because this is actually given. And the function prior, which we can do something about. So the first, D given F, this is what is called the likelihood, and the probability of F, and this is actually called the function prior, right? What kind of information do we know about the function that we're trying to optimize? We try to encode this in a function prior. The second part is the acquisition function, which is very important that now we have a model. How can we navigate this space to maximize the model? So we need something that will give us a direction, and we use the acquisition function for this. Okay, for function prior, if you go through the Bayesian optimization literature, one of the most widely used is the Gaussian process. You can think of Gaussian process as a generalization of Gaussian distribution. But instead of giving you a mean and a variance, it gives you a function of a mean and a function of a variance. So that's the big difference. So if you look at once we have this Gaussian process as a function prior, we can build the model, the posterior distribution, in a closed form. And yet it looks scary, but it's actually very intuitive. So the first mean of xt plus 1, which is what is the expected value of the function that we're trying to optimize at xt plus 1, is given by this closed form. And what kind of uncertainty do I have around this point? So sigma xt plus 1 is given by this formula. So don't worry about it. It's just an open source library that you download and then you just optimize and then does optimization. But anyways, so don't worry about it. What I need to talk about is K. So basically these two formulas is dependent on K, and what K does is it's a way that we can encode some information about the points, the relationship between the points that we're trying to use. So the input for this function is regions, right? For our case is regions. So we use this matrix to encode some information about the regions that we know, right? So I will talk about this later, but anyways, just keep in mind that K is kind of a way to encode some information about our inputs and, of course, the output, which is the function, right? Okay, that's the first part. So we built the posterior distribution, and then we need to use an acquisition functions. And again, the literature is full of, a lot of acquisition functions. So basically, it helps us to search for the optimum. So and it is designed in a way that higher values for the acquisition function usually correspond to higher values for the objective function, whether it's a high prediction, like it's a high classification score for the object, or it's a high uncertainty, or both. So I will talk more about this part. Again, another scary formula, but again, again, you don't have to work this. Just an open source library that you choose what kind of acquisition function you want to work with. But anyways, this one just gives you the difference between mu x and fx star, which is the best region we've seen so far, and x is the current region that we're trying to test. So it gives us the difference between those two values. So now we want to improve the classification score, so we want to go for regions that give us higher value for the first term. And the second term is the uncertainty, which it's commonly known in trying to optimize is try to balance between what's called exploitation and exploration. So exploitation is, I know this region will give me higher scores, so I will keep going in this direction. Or exploration, I have a lot of uncertainty, I don't know, so I'm going to go for the exploration phase, right? So this function tries to balance between both, between uncertainty and high return. So that's basically it. Okay, so try to put this all together. Is we have an image X, we have a classifier F that give us the classification score, and we have like a set of regions that we already observed. We already know the score for, which is dn. You can start from line 3 here. It's an iteration until t, until the money is out, or the budget for optimization is out. You do the following. You start with an empty set of proposals, right? And then for all the regions that you have observed so far, right, you have y is the region coordinate, and f is the score of this region, line 5. So we go ahead and we build what is called the local neighborhood around this region. We push this to acquisition function. I ask it to give me the next best region. It's y hat, line 7. And then at line 8, I observe the true region score from this CNN, which is f hat, and then I update my proposal set with this new proposed region, and I continue doing this. So I have a nicer representation for this guy. So let's say that I have this is the classification network, the dashed line, right? The x-axis is the regions, the coordinates of the regions, and the y-axis is the score of each region, right? So I observed first set of regions with the blue circles. This is the true values. And then I fit a model. That's the posterior distribution we talked about, right? And when you fit a model, you see that at the points that you observed, there is no uncertainty. The uncertainty is quashed. But the points that you haven't observed, hence this shaded purple part, is where the high uncertainty lies, right? Because you haven't seen any points around this. And that's where the model is uncertain. Then we introduce the acquisition function, and you can see that at this almost in the middle, the acquisition function gives me the highest value, so I will pick the point at this location, right? And then I will observe, and basically you see the model is squashed. So now I know for certain that this value is true. And then you keep repeating this, right? So another example. So we start with a lot of regions. We pick the best regions, the ones that have the highest scores, and then we build this local neighborhood around it. And then we ask the acquisition function to give us the new region, and then we observe the true score of the new region, which is higher, and we keep repeating this. We build the dlocal, we acquire, we get a new region, and so on and so forth. So we move from the first best region to a better regions as we do more iterations of this algorithm. So typically, we used faster RCNN for these experiments. We use the ZF architecture. It's quite small architecture that fits into my GPU, basically. That's just some details for people who use faster RCNNs. So we just mentioned that. So if you can reproduce the results. Typically, when you want to benchmark, you use data sets that are used for benchmarking, and in this case, we used Pascal VUC 2007. It's broken down into 5,000 images for training, 5,000 images for testing, and it had almost 20 different categories. Yeah, so the first experiment was, as I said, try to integrate the faster RCNN with this open source Bayesian optimization library called Robo. And we did that, and you can see here the faster RCNN ZF architecture is the benchmark, and then we had the integration with Bayesian optimization, and you have almost 20 categories. The metric we're using is called average precision, right? And this is typically widely used in doing object detection. So the higher is better. And you can see that we either went head-to-head or we even made a higher average precision. And the last one is the mean average precision over all the classes. You can see that the integration went even higher. So in this Pascal VOC dataset, if you have 1% higher, you publish, basically, because it's quite difficult dataset. Now back to the K matrix that I talked about, which we encode some information about the regions that we're trying to do. And we here used what is called Mattern52. It's the default value for Robo, so there's nothing magical about it.
What is the value there? The percentage cover as compared to the perfect space.
I'm sorry?
What's this number mean?
This is the metric. This is the average precision metric. So basically, you average the precision of the detection along different recalls. Not the perfect one. So the first line is faster RCNN, so using the same metric, and the second line is the integration. So we try to compare this to the baseline. We compare to those two guys.
What will be the one mean?
Perfect.
Yeah, so that is.
Yeah, but we try. We're not.
Means you are like 60% cover compared to the perfect.
Yes. Yeah. Exactly. But we're trying to compare to the baseline. So. Okay, so the second experiment was to use a different kernel to encode this kind of information. And since the input of our optimization is regions, so it's quite intuitive that when you move the regions apart, the score should be different. The classification score should be different, right? So we use this exponential squared kernel to describe this, and basically what it does, it gives you a higher correlation coefficients when the regions are very close by, and once you move apart, this start exponentially to decay, so the correlation coefficients decays. And again, the same metric, the same baseline, but different kernel function, and you can see here that we almost 1% we beat it. So for example, the boat category, you can see that it's almost 10% higher, so it's quite improvement. And this is just some quantitative results. So the red boxes is the faster RCNN. So that's the localization given out from the faster RCNN. And the green boxes, the green boxes is ours. So that shows you, the difference between the accuracy of localization for the objects. Yeah. So we talked about faster RCNN, deep learning, object detection. Talked about Bayesian optimization, and we showed you the search algorithm and eventually the results. So that's it. Any questions? No.
Besides Bayesian optimization, are there any other optimization?
Not of what I'm aware of. But this is, again, this is black box optimization. This is not like a general purpose optimization, because in this case there's a bunch of techniques that you can use to optimize. But this is a black box. And in terms of when it comes to a black box, I think Bayesian optimization is the most widely used. Yeah.
How far does it run? How does it compare to actual training time?
So there's no free lunch. So basically, when you start introducing this kind of complexity, you have to sacrifice something, and in this case, it was time. Yeah. So compared to faster RCNN, it took the execution time down a little bit. But again, this can be optimized because we're doing this optimization on the CPU, right? And the whole detection pipeline on the GPU. So you had to move the data in between. But once, for example, you move to a different model, instead of using Gaussian process, you use Bayesian deep learning network, then you will do the optimization as well on the GPU, and then hopefully the time gap become more smaller. So basically that's scratching the surface of this idea. Yeah.
As I know, next iteration after RCNN, fast CNN and faster CNN was YOLO and YOLO 2.
Yeah.
Did you compare it to YOLO and YOLO 2?
That's a very good question. So if you look at the object detection literature, you can divide it into two branches. The region-based branch, which is RCNN, fast, faster, mask, all these kind of ideas. Basically, this reincarnation of RCNN, basically. And then the second branch with a single shot, like YOLO. But in YOLO, there's no regions. So this whole idea based on regions. So that's why we didn't go through this YOLO comparison, because basically YOLO does not have region. It's a single shot from pixels to objects. That's why. Yeah. Go ahead.
I'm just curious now. Do you think this could work for a segmentation problem? So there's something called mask RCNN.
Yeah.
And I guess in that kind of problem, it's really important to get the bounding box really close so you can segment the pixel.
Yeah. So I haven't looked at this actually, but it could be, yeah. So basically, it could be, but I haven't went through this path yet. No. Any other questions? Yep.
Maybe I misunderstood, but I thought you were going to talk about transforming data into like an image so that you could use these techniques, but it was not image data, it's other data.
Yeah, no, but no, we didn't have this intention. I think Rocky just mentioned it as a a byproduct for this kind of work, that you can actually apply CNN on different on a different space like bank transactions. But we didn't plan for this talk. How to transform.
If you like, we might able to arrange another one in some time in the future.
Added to the wish list?
I'm sorry?
As it added to the wish list?
Yeah, exactly, yeah. Yeah. Okay. Thank you, guys. Thank you so much.